And this is, and I've got a co-host who's hopefully online, who's going to be introducing our speakers.
I am online, Alison, but my video will not come on because the host has barred it.
Well, welcome to our meeting. Would you like to would you like to take the virtual stage and introduce our speakers? Thank you very much.
Yeah. So, Kaundi, if you can enable my video. I think now it's there. Good morning. I'm sorry I'm missing out a nice workshop in even a nicer place. So it's my pleasure to introduce the next two speakers. One is Divyanshu Mishra. Divyanshu is working as a data scientist at the THSTI in India. His interests are in the field of medical image analysis and particularly ultrasound images and videos. And he's trying to solve problems related to anatomy detection, class imbalance, federated learning, and multitask learning. He believes that the translational research is an important one and is aiming to develop AI-based tools to aid medical professionals so that they can provide better patient care. The second speaker, I believe, is Pramit Saha. He is a DPhil student under Professor Alison Noble in the University of Oxford. His doctoral research is also aiming at solving the challenges encountered in federated learning scenario, including issues like class imbalance, non-HD, non-IAD, data distribution, etc. This is, of course, towards facilitating multi-institutional collaborations without sharing patient data, in other words, protecting their privacy. And Pramit has done his master's from University of British Columbia. And for the work he did there, he was given the prestigious Young Scientist Award by MICA Society in 2020. Over to you, Divyanshu and Pramit.
Hello, everyone. I'm Divyanshu. I'm a data scientist at THSTI, as ma'am mentioned. In the first part of the talk, my colleague Pramit will be presenting something, and then I'll be following up. So I'll just go and sit, and you can watch him take you through federated learning and what it is.
Hello, can you hear me?
Yes, we can hear you, Pramit.
Okay, great.
Yeah.
Okay, thank you. Hello, everyone. A very good morning to all of you. I'm Pramit, and I'm joining virtually today from the Oxford, UK. So in the two earlier talks today, we heard about data bias and domain adaptation, which deals with aligning a source data distribution to a target data distribution. In this talk, we will focus on data privacy and data governance, which is another important topic in the context of machine learning. So in this presentation, we'll be examining an approach different from centralized machine learning. Jointly with my colleague Divyanshu, we will be talking briefly about a relatively newer learning paradigm called federated learning and how it solves the data sharing bottleneck, particularly in the context of medical applications, while still maintaining the privacy. It has gained quite a lot of attraction in the last couple of years for good reasons. So first, I just want to briefly introduce federated learning before even I go into the contents slide. So the basic idea can be summarized into one sentence. instead of bringing user data or medical institutional data to a centralized location or server, which is shown in the middle of the figure, we bring part of the training and prediction procedure to the user's device or the institution possessing the data, whom we call the clients or the edges or the nodes, as shown in the four corners of the figure here. So that's what federated learning is all about. Now, here is a brief roadmap of today's talk. Well, there's a lot to talk about federated learning, but here we will just focus on the key aspects as a sort of introduction to the area. So we'll be starting with the motivation behind federated learning and discuss why we should care about learning this paradigm at all. Then we'll discuss about what federated learning is and how it works and explain a basic federated learning algorithm. We'll then see what are the main challenges or active research areas in the field of federated learning, and then we'll conduct a small experiment to show how to do federated learning in practice. At this point, I'll pass it over to my colleague Divyanshu, who is present in person, and he'll be able to demonstrate how to run federated learning algorithm with a small subset of a computer vision dataset. We'll see how it compares to the normal centralized learning scenario. And for those of you who are new to federated learning, we'll then refer you to some good resources for both reading and for implementation point of view, which can start as good, which can act as good starting points. And finally, we'll conclude our talk with some key takeaway messages and go for Q&A. Okay, so let's get started. Deep learning, which is a branch of machine learning and AI, has emerged as a core technology in problem solving, owing to their fantastic capabilities of learning from the data. But deep learning approaches are known to be notoriously data hungry. It generally needs massive amount of diverse data to generalize and perform well on real world applications. The progress of deep learning, as you can see from this graph here, is highly dependent on the premise of availability of large amount of training data. Without massive data, the success of deep learning in large scale is uncertain. Now, standard machine learning approaches require centralizing all the training data in a common place. This is called centralized machine learning scenario, where the model and the data are at the same place. The idea is to collect all the data and store it together and train a model on all the accumulated data. However, in many scenarios, particularly in healthcare, due to data sharing restrictions and privacy requirements, it is not always possible to collect all data from the institutions across the countries to store in one central server. Centralizing or releasing data poses not only regulatory, ethical, and legal challenges related to privacy and data protection, but also some technical ones. Like anonymizing, controlling access, and safely transferring healthcare data is non-trivial, and sometimes it's an impossible task to do. On the other hand, the promise of federated learning is simple: to address privacy and data governance challenges by enabling machine learning from non-co-located data. So in a federated learning setting, each data controller not only defines its own data governance processes and associated privacy policies, but also controls data access and has the ability to revoke it. And that's exactly why we should care about federated learning, as it has an immense potential to help collaborations in healthcare. So what is the basic framework of federated learning? As I kind of introduced it already in the first slide, federated learning framework involves server and clients. So the client devices will receive a training model, that is the model parameters shown in red dots. These devices train on the local data, which usually just takes a few minutes. The devices then send updates on the parameters to the server, which is located at the center here, which is basically the updated gradients as shown in with the help of the blue dots here. The server then aggregates the updates it receives from the devices to perform one update to the current model. And the new updated model is then sent to the devices for a new round of training. The frequency of the updates and the selected number of clients can be adjusted based on the requirement. And as evident from here, there is no requirement of data transfer at all. Okay, so here's a simple animation that shows what's actually going on with the server and the 4 nodes or clients in each round of communication. So here you can think of the black lines as some sort of decision boundaries if you're thinking of a classification problem, or you can think of them as linear fits if you're thinking of a regression problem. So the black lines basically show the model performance, and the white dots are the data points. So as you can see here, there is no data in the server at all. All the data sits in the local client's devices and never leaves the device. The server sends out the model, which is trained separately, yet simultaneously on these 4 different datasets in 4 different institutions. These models are basically personalized models that work best for the respective clients, but fails to generalize because of the heterogeneous nature of the data distribution across different clients. So for this, we need a global model. That's why the weight updates of each of the models are then sent back to the server, as I mentioned earlier, and then accumulated based on some particular algorithms in the server side, which results in the global model that should ideally work for all the clients. So now that brings us to the basic federated learning algorithm, which was published in AI Stats 2017 by Google. It's called Fed average or federated averaging. This slide is a little bit more mathematical. It's more of a technical diagram of federated learning procedure. So the networks in the figure to the left basically represent deep neural nets, and W represents the parameters, which are basically the weights in the context of neural network. Let's say there are capital K number of clients, and at the Tth round, the learned weights of the neural network are represented by WKT, where K denotes the kth client. The basic idea is to average all the weight updates received from each of the clients at the server side. In practice, the participants are likely to hold an unequal number of data. So to account for this, the local models are aggregated by weighting each local model by the number of available training samples, as depicted here in the right. So NK is basically the number of data samples present in the kth client, and N is the total number of data samples present across all clients. This weighted average yields the central model parameter for the T+1s round, and then they are sent back to the clients again. Thus, models of participants holding higher number of samples are taken into account more than the ones holding this few. While this strategy does sound very simple, it has shown to work very well in federated learning use cases. Well, there are more than 100 federated learning basic algorithms by now, but at least 45 among 50 federated learning papers published in medical image analysis area just use this exact algorithm for aggregation. So this is definitely a good starting point if you want, if you're planning to get started with federated learning. Now, one important point is that the fundamental optimization technique used in centralized learning is stochastic gradient descent, or SGD. But there's a difference between a naive federated learning extension of SGD and Fed averaging, which is that Fed average performs a local number of updates within the client before doing the averaging step to reduce the communication time. So this leads to a major speed up, but at the cost of complexities related to the optimization, because the convergence isn't straightforward as SGD anymore. And there's ongoing research going on in this direction. I should mention here that the general federated learning algorithms have an intermediate step of selection of a fraction of clients from thousands of clients. For example, in the case of mobile devices, our mobile phones. For our case, however, we don't realistically have collaborations with thousands of hospitals or medical institutions. So the client selection step is not as relevant for us, and hence I have omitted it from the presentation, as we basically deal with cross-silo federated learning, which only has a few clients. So there's no question of selection. So now that we know what federated learning is all about, let's briefly discuss the active research areas in federated learning. So it is an emerging area and has three main areas of research. The first one is the effectiveness of the algorithm, which stems from the fact that the data is generally highly heterogeneous. The data distribution and characteristics widely vary from one client to another, depending on the collection protocol, the subjects, the data acquisition devices, and so many other factors. So now we are dealing with non-IID data where many of the basic assumptions of centralized machine learning don't hold. Another related problem is class imbalance, where each client has different class distributions. For example, in a particular client device, that is in a particular institution, the number of diseased subjects may be way higher than the normal subjects due to the outbreak of a disease in the locality. But this might not be true for the other clients, which might have much less disease candidates. So there can be different scenarios of local and global imbalances like this. Similarly, there can be something called client imbalance related to the fairness allocation problem. In other words, a big medical institution with lots of data might be dominating the algorithm and drifting the optimization point towards itself, whereas the data from the other smaller institutions may not receive equal importance, not because they are not vital, but just because they have less amount of data. So these are some of the issues that need to be addressed yet, and research is going on in this area. The second branch of federated learning research is communication efficiency. So it's a more practical aspect where communicating with hundreds of devices at the same time simultaneously can be quite tricky. So each client has different amount of data, computational resources, etc. So communication might not be synchronous. Some devices might be slower than others. Other devices might drop at the beginning, at the middle, or at the end of the training process. So this is known as the straggler effect, and it's an ongoing research topic, how to deal with it. The third branch is related to privacy. So though we are not directly sharing the patient data with the server, we are sharing the gradients or the weight of dates, which have a lot of information about the input data. And in some specific cases, it's somewhat possible to reconstruct back some of the representative samples of a class of a data set. So to prevent attacks and information leakage, there are ongoing investigations on differential privacy related methods in federated learning. So this brings us to a sample experiment that Divyanshu is going to demonstrate now to show how to conduct federated learning in practice. So over to Divyanshu.
Can you hear me? Yeah. So thank you, Pramit, for this theoretical introduction. Now I will be taking you all to a practical aspect of federated learning, where we will be basically looking at some code. So I'll be comparing with like the centralized learning. I'll be first demonstrating what centralized learning is and how you can basically train a normal centralized algorithm, which might have few of you might know if they're working on the research area. And then I'll be showing that how you can quickly convert a normal centralized algorithm to a federated one. So next slide, Pramit. So yeah, as Pramit said, that in centralized learning, we have the opportunity, or it's an ideal scenario where we can pull data from all the clients from various institutions. And yeah, so to demonstrate that, I'll be using a computer vision data set known as the Saha data set. It is a very simple data set which comprises of 10 classes, which are plane, car, bird, cat, deer, dog, frog, horse, ship, and truck. So basically, the task is that given an image of one of those categories, the model has to say that whether a particular what object is present in that. So we call that task as multi-class classification, and that what I will be demonstrating. So to do that, I'll be using 30,000 examples, and we'll be considering that this is the complete example set we have available with us. Like we have pulled from different clients as it is shown, And then we're creating a master data set. And we'll now be training an algorithm. Pramit, next. Yeah, 30,000. Yeah. So first, let's go through a simple line of code. As you can see on line 20, I'm using a simple, so for the coding this, I'm using a PyTorch framework. And I'm using a PyTorch Lightning, PyTorch Lightning wrapper. So to demonstrate, I'll be using a small model known as a ResNet, a small deep learning computer vision based model, which basically, as is defined in the step, which is like 31st line, will be taking an image and label as input, and will then passing the image to the model, which is a ResNet 18 model, which takes a 32 cross 32 image as input, which an RGB image, and predicts the probability of one of the 10 classes, which I mentioned before in the CIFAR 10 dataset. Once we pass through it, it actually returns a vector of the number of samples cross 10, which basically gives the probability of each of the classes. Like it basically says in this particular image, how much like if cat, what is the probability of a cat being present, and so on. We then pass that vector to the loss function, which is given by 33, and we'll be using a simple cross interval loss function. And it is basically calculating the loss. It says that loss with respect to the true label. And we basically are trying to find that whether a model is making a correct prediction or not. And we then use that loss to guide the training. And this process repeats, and our main aim is through the Adam optimizer, which is shown as in the line 27. We are aiming to reduce the loss, so the which basically says make the model perform well on all the classes. And so that will be this process will be repeated until a satisfactory performance is reached, which we can in this experiment we'll be doing for 20 epochs. But if somebody is training it, they can track the on line 35. There will be like an accuracy or some metric they want. Like if for some cases they need the accuracy or something, they can track and train accordingly. Pramit, next slide. So yeah, can you start? Yeah. So basically, I'll start a centralized training, and it will take all the data from all the servers. So and it will start. So it will actually train for 20 epochs, but as we don't have that much of time, I'll be just demonstrating some of the phases. Like in the starting, Pramit, can you go to the end? Yeah, it's in the last epoch, and it's training. So it like trains for say 80% of the time, and then we have an internal validation set and an external test set. So it will first validate on the internal validation set and report some accuracy on the left. And then we have a test set, which is same for both the federated case as well as the centralized case, so that we can compare performances. Pramit, yeah, Pramit, can you go back?
Go back.
Yeah, and at the last, just show the final accuracy. Yeah.
That's it, I think, here.
Okay, no problem. Can we go to the next slide?
Yeah.
So in this, actually, we get an accuracy of 68% on the global model using all the data. And now we will be coming to federated learning, which Pramit just discussed, where instead of taking all the data and sharing it, where we have like data sharing restrictions can come in because it's a practical scenario, or privacy concerns. Or there's another thing that Chen mentioned, that even though that we will have like access to data, but the data might not be variable and not capture the entire population. And so that's why also federated learning is important. So to demonstrate that scenario, I'll be again using the CIFAR 10 data set. But this time now I will not be using the entire data set at the centrally, but instead will be like simulating two clients, say THSTI or Oxford, or just two clients, where we will keep like half of the data is available at one client and half of the other. So for each client, we'll be having 15,000 samples. And there is a concept of local epochs, which basically means that we train the local models for a fixed number of time, and then we share it to the server. So that fixed number of time is actually the local epochs before it's sent to the server for aggregation, and then it's sent back like it's shown in this figure. And then I'll be using training it for 4 rounds. So 4 rounds of local training, then aggregation, and then again. So it will happen for 4 rounds. So if you compare globally, the complete training will be happening for like 20 epochs. Next slide, Pramit. Yeah. So to discuss the code, I will first start with the server code. So as Pramit mentioned that for the server, we use various algorithms for aggregation. So basically after the updates are sent to the server, how can we aggregate and combine them? So to make the global model and then send back to the various clients. So the people who are like using or training and code, they can either choose to use the federated averaging algorithm like Pramit mentioned, which is very good, or they can design their own. In this case, we'll be using the federated averaging with some parameters. Like we are saying that we will just train like 50% of the time we will train, and then we'll 50% of the time we'll test or validate. And we have taken minimum clients to start the training. So basically, you have this server, and then in the server you have to connect say n number of clients before the training starts. For that, we are keeping it just 2 clients, but people can take like if it's a big prediction task or something like Google uses keyboard prediction. Basically, they use your mobile data. I don't know if you know, but when you are charging your phones, federated learning is actually happening at the background. When you put it on charging, it will use your data, which is like you are typing on the keyboard and it predicts something, but you might choose it and you might not choose it. So it uses that data to train a local model. So you can use that, and so a large number of clients will be there. So you can decide how many clients you can take. And also, as Pramit mentioned, basically how many clients to sample. Currently, we are sampling, it's not written, but currently we're sampling 100% of the clients because we have limited number of clients in medical setting. But if you are doing some large scale Google or something, they also have a sampling rate. Say you can put a sampling rate of 50% or something. So, and then that's it. That's just a small code, and you can for the server. And to run the server, it basically runs on a IP address. Currently, we are running it locally, but you can use some IP address. Say that say you choose to, in our scenario, we choose to have the server at THSTI, and the local clients were one was present at THSTI and the other one at Oxford. So we had a particular IP address which was public, and we all can connect it without any problems from any geographical location. So that is where the server address goes in, and then there are various configurations, like you can take the number of rounds and all that, and provide the strategy, of course, like we are using the federated averaging. Pramit, next slide. Yeah, and then in the client side, as you can recognize, this entire code on the left is from the last centralized example. So it doesn't need any much of the changing, except we just need 2 functions to be exact, which is the get parameters and the set parameters function. And what it basically does, as the federated framework is there, after fixed number of epochs, you have to send your local epochs. You send your the clients need to send their models to the server. So for that get parameters function is implemented in each of the clients, and after fixed number of rounds, it send the model to the server for aggregation. Similarly, for set parameters is the so after the one round is complete, the latest model is sent back to the server, and for that the set parameters function is used, which basically sets the current model with the latest parameters. And then it is just for a completion. So this complete model will be called there as a model, and you can define like how many, for example, we are using 5 local epochs. So we can define 5 number of local epochs and the length of various train and validation data loaders. And so self.get parameters function is called after every fitting cycle to send the weights to the server, which was defined previously. Pramit, can you play? Wait, don't play. So I'll just introduce. On the top 2, they are client 1 and client 2. And in the bottom, you have the server. So we have started the server. And what the server initially does, it requires some initial parameters to start. There are 3 choices you can do. You can either take a pre-trained model if you already have, like if you have some model, centralized model which is trained on your own data, and then you can build upon it in the federated fashion. You can do that. So it initialize global parameters. We use a sampling strategy, which it basically samples from one of the clients, and then the server has that parameters now. Pramit, yeah. So now each of the client will start training the local epoch to collect to the server, and it will start training for the local epochs, and it will train for like 5 epochs. Pramit, just first finish the first round a little bit. Yeah. So at the end, as you can see, after Pramit, can you just hold the slide for a minute?
Okay, just a moment.
Yeah, thank you. So in this, as you can see, what is happening, if you can see here after echo starting, basically the server is sampling 2 clients out of 2, and then it training goes on, and then there is a fit round where basically 2 of the results are sent back to the server and it's aggregated. And the same thing is happening again and again until the last round, which Pramit will just show. So this is the last round which is going on, and the model is validating on the test data set. It's testing, and yeah, it will finish and the server will disconnect soon, or disconnected. Yeah. So as you can see, we are getting an accuracy of around 65% with using Pramit, can you go to the next slide? Yeah. So we are getting an accuracy of 65%, which with using just 50,000 examples, like at each side, 15,000 samples at each side, instead of using the entire at the particular slide. So that's how, even though it is a little bit less than centralized training, but it actually builds a model which is more generalizable. If we currently we are using a subset of the data set as a test set, but if we have a global test set, the performance of federated learning can even surpass the centralized learning. And also it gives people opportunity to like build models even if they have if they don't have large number of samples available at their site. So that will be my presentation, and I'll pass back to Pramit, who will give some examples.
Thanks, Divyanshu, for the demonstration. So in kind of the same way as Divyanshu explained, we ran federated learning algorithms with 4 clients in total. Client A1 and A2 on the Indian side, and client B1 and B2 on the UK side, for a task of fetal ultrasound video-based anatomy detection. As of course, data sharing directly between these 2 countries were not possible. We found that we were able to detect the fetal head with 88% accuracy, dividing the data into 2 clients, and 85% dividing the data into 4 clients, 2 in Indian side and 2 in UK side. Under the same settings, the abdomen detection accuracy was 79% and 70% respectively. So this kind of shows the feasibility of the approach in multi-institutional collaborative learning. For those of us who are getting started or want to get started with federated learning, we thought it would be nice to have a resources slide. So there are available frameworks that help us conduct the federated learning, the communication between the server and clients, and the training. The simplest, I think, is Flower, which we used for the demonstration today and in our experiments. There are others like PySit, Fate, and the others tabulated here. Each of them specialize in different aspects. So you can choose the platform based on your particular requirement and problem context if you want. There are quite a few good blog posts out there. I personally found the ones by OpenMind, NVIDIA, and UC Berkeley to be quite good. They're quite informative, yet not too hard for a first read. So to conclude, we presented the main idea and the basic algorithm of federated learning. We gave a brief demonstration and discussed the main research areas in federated learning. It is to be noted that federated learning is an emerging area. So not all problems we discussed have already been solved. We ourselves, as a part of the Calopus project, are endeavoring to solve or address some of the questions in the context of medical image analysis and fetal ultrasound video anatomy detection. As you can see the graph here, there's a sharp rise in the number of federated learning papers lately, which shows the growing interest in this field. Federated learning is a secure way of collaboration. It is a distributed and flexible learning paradigm that has the potential to enable multi-institutional collaborations by skipping the complexities related to data sharing. Okay, many thanks to everyone for listening. If you have any more questions, please feel free to ask now. If you have further questions or queries or interests in the area, please feel free to drop an email to Divyanshu or me. We'll be happy to hear back from you.